Pues, bienvenidos. I speak in English. So it's a big pleasure. It's a big pleasure to introduce this seminar given by Sabrina Keil. Sabrina Keil is German. She's a postdoc at the Department of Earth and Environmental Sciences, Geophysics of the Ludwig-Maximilians-University in Munich, also abbreviated LMU. Thanks to an international agreement between our institute and LMU, she is spending now half of her time at our institute. Okay, so she's on the third floor, so you can speak with her and later on also for discussion. She's presently doing research on seismic interferometry to characterize the shallow subsurface of the moon. And her PhD, she finished in 2023 in Munich, evaluation of ground motion and optimum seismic monitoring at an inner city deep geothermal power plant. By the way, I hope she doesn't kill me. This is a thesis she did by cum laude, and it received just recently the best dissertation award of the entire geoscience community in Munich and around. Her master she did also in Munich on rotational motion sensors. A very interesting subject, especially for us here. Also, it's a very new subject because we also would like to enter into rotational seismology. And she will also talk today a little bit about rotational seismology. So, Sabrina, wann immer du möchtest.
Yeah, thank you, Martin. So first of all, I would like to say thank you for the opportunity to be here and give this presentation. So like Martin said, what I'm going to present today was done during my PhD, which I just finished last summer at LMU. And during the presentation, I will put some special focus on what we're specialized in Munich, which is rotational seismology. So the project here was part of the so-called SAIGA project, which was a larger project concerned about induced seismicity due to geothermal energy production in Germany. And it was conducted with several German universities and research institutes. So already 2 weeks ago, we heard something about geothermal energy. So you're probably familiar with some of the terms. But anyway, let's take a look again what geothermal energy is. So here you can see a simple sketch on how geothermal energy production works. So in general, we have a reservoir depth, which either already contains hot water or, like in enhanced geothermal systems, water is pumped into a host rock, which creates cracks, and therefore the fluids can circulate and heat up. And then you have a production well, where the hot water is pumped up and then used for heat or electricity generation, and then an injection well where the cooled down water is pumped back into the reservoir. So you see it's kind of closed loop, and this form of energy production is nearly carbon-free, it's sustainable, and it's available year-round. So it does not depend on weather conditions like for wind or solar energy. However, the drawback is that this process can induce earthquakes. And in general, these earthquakes are relatively small and are often not even felt by the population. But there are some negative examples that show that larger magnitude events can be induced. And one of these examples is South Korea, where an earthquake with magnitude larger than 5 was triggered, which caused destruction and also injured people. So of course, this leads to public concern and also the shutdown of geothermal projects. Therefore, managing the induced seismicity risk is crucial for the further development and exploitation of this form of energy. Hereby, several open questions need to be answered for the development of proper risk governance strategies. And one of the first questions is there the risk of wave amplification? Because soft sediments can amplify seismic waves and therefore cause more damage compared to sites on firm bedrock. So we need to get more information about the shallow velocity structure, and this is usually done in so-called microsonation studies. The second question is, what is the distribution and the maximum ground motion in case of an earthquake? This is already important to evaluate during the planning stages of a geothermal project, but of course also after an event in order for authorities to make fast decisions, especially if the event was damaging. However, in general, this is difficult to evaluate since generally we only have few seismic stations in the vicinity of our geothermal power plants, and therefore a spatial interpretation of the ground motion is difficult. And I will show that seismic simulations can help here. And the last question, since I've already mentioned the monitoring network, not only the sparse number of stations poses a problem, but especially also the high ambient noise levels, especially in urban environments. And therefore, the question is, how can the seismic monitoring network be improved in order to detect small magnitude events? And here I will show you a network optimization approach based on surface and borehole stations. So in the following, I'm going to answer these three questions on the example of the wider Munich area, because here there are a number of geothermal power plants in operation. So Munich is located in the south of Germany in the so-called Molasse Basin, which is a foreland basin north of the Alps, and it's filled with up to 5 kilometer thick sediments. So as you see, there are many geothermal projects surrounding the city, but since recently, there's also one in the middle of Munich, which is to that point Europe's largest inner city deep geothermal power plant with a total of 6 wells, so 3 production and 3 injection wells. And it provides heat for 80,000 people. The reason why we have so many geothermal projects in the area is, well, the area is well suited for geothermal energy production. So here I show you a cross-section through the Molasse Basin, so from north to south. And you can see that there's a reservoir depth, which is dipping from north to south. And in the area of Munich, this reservoir reaches a depth of about 3 kilometers, which gives us water temperatures of 100 degrees, which makes it suitable for geothermal energy production. However, induced seismicity was measured at some of the geothermal power plants with magnitudes up to 2.4, which was also felt by the population. And that, of course, raises concern about induced seismicity at this new geothermal power plant in the city. And if something would happen there, of course, a lot of more people would be affected. And that's why it's so important that we're answering these three questions. So first, do we have amplification effects since Munich is underlined by sediments? Second, what is the ground motion that we expect in case of an earthquake? Do we have the risk of damage to buildings? And how do we improve the seismic monitoring since we have relatively few stations and we're located in the city, so we have high ambient noise levels? So let's start with the first question about the amplification effects. So to answer this, we need to get more information about the shallow velocity structures. And to do this, there exist a variety of methods. However, the most common ones are passive methods, meaning that they're measuring ambient noise. And since we're located in the city, we're talking about anthropogenic noise. So these are vibrations caused by cars, train, construction works, industrial operation, and so on. And these signals have relatively high frequencies of 1 to 20 hertz. And they mainly contain surface waves, so Rayleigh and Love waves. So just a reminder, Rayleigh waves cause an elliptical particle motion, and Love waves cause a transverse particle motion. So in the following methods that I'm going to show to you, we're always measuring these types of waves, so you should keep this in mind. So one of the most common methods to measure these waves are array measurements, where you set up a number of seismic stations, for example, in a circle, and then you can measure the direction of the incoming wave and the velocity through the arrival time delay of the wavefront at the different stations. From this, you can compute so-called dispersion curves, which show you the velocity of the wave depending on the frequency. And then in the next step, through inversion of these dispersion curves, we obtain our 1D velocity profile. So these array measurements are well tested and well understood. As we see, they give us dispersion curves, and these can then be inverted for a complete 1D velocity profile. However, the drawback is that you need a lot of space and also time in setting up all these different stations. And then especially if you're working in a city, you often don't have the space to build an array. And therefore, single station methods are more desirable. And here already the method of horizontal to vertical spectral ratios exist, which is a very easy method since you only need the recordings of one instrument. So in general, this H/V ratio is computed from the ratio of the Fourier amplitude spectra of the horizontal over vertical particle motion. And what you get are these H/V curves here, and in the best case, they exhibit a pronounced peak, which is related to the resonance frequency of the site. So this gives you information about the depth of layer boundaries. As I said, this method is really easy. However, its theory is still not completely understood, and the results suffer from non-uniqueness. And that's why we wanted to develop a new single station method, so-called 6C method. This combines 3 translational components that are typically measured by a seismometer, but also 3 rotational components. So first of all, you have to know that a seismic wave does not only cause translational motion, but also rotational motion. And I will show this to you in this simple animation where you would see different wave types coming in. So first P waves, then SV, SH waves, and for us most important, Lough and Rayleigh waves. And then in black, you can see the 3 translational recordings, and in red, the 3 rotational recordings. So let's start the animation. So first, you will see the P wave coming in, and you mainly notice the translational motion. And the same also holds for the SV type and SH type waves. You only notice a translational motion. Now this changes when the surface waves come in. So here for Lough waves, you will notice a strong rotational component, and the same also for Rayleigh waves. Now, when we take a closer look at the recordings, we can see that Lough waves only cause a rotational motion on the vertical axis, and Rayleigh waves cause a rotational motion only on the horizontal axis. So this is a really important finding because now we can use these 6C recordings to differentiate between different wave types. And we can also use it to compute the phase velocity of these waves. For example, for Lough waves, it was found that the phase velocity can be easily computed through the ratio of the transverse acceleration, which are these 2 components here, and the vertical rotation rate, which is exactly this component here. And a similar relation is found for Rayleigh waves, where you would take the vertical acceleration and the horizontal rotation rates. So this is really nice because now you can see in the formula also the phase velocity is frequency dependent. So also with this method, we can compute dispersion curves using a single station measurement. Well, until recently, it was quite difficult to measure these rotational motions. But now there exist rotational motion sensors that are sensitive enough for these kind of applications. And here you can see the measurement setup that we used. So it's quite simple since we only need 2 instruments. So 1 regular seismometer and 1 rotation sensor. And we place them on a common plate to make sure that they're recording the same motion. So this really can be seen as a single station measurement. And as I said earlier, from this we can also get dispersion curves, which then again are inverted for the velocity profile. So in our case, we're using the BlueSeis 3A rotational sensor, which is based on fiber optic technology. This makes it completely insensitive to translational motion, which is a great advantage. Here you can see a simple sketch on how the measurement principle works. So in general, you have a fiber optic cable, and in the cable you have 2 laser beams that are propagating in opposite directions. Now, when the laser beams meet, they cause an interference pattern. If the instrument is completely at rest, both beams have the same path length, and therefore the interference pattern stays constant. However, if a rotation is applied, one of the laser beams will have a shorter path length, and therefore this interference pattern changes. And this phase shift can be measured by the instrument, and it's directly related to the rotation rate. And that's how we then measure our rotation. So at this point, I want to make a small excursion and show you some other applications of rotational seismology. So what can we do if, in addition to the 3 translational recordings, we also have the additional observable of rotations? So the first thing that I already said is 1D inversion, which I will also show you a bit more in a bit. Besides computing the phase velocity of the wave, we can also compute the direction of the wave, so the back-azimuth, where the wave is coming from. And that could be, example, used for source tracking. So imagine you have a seismic signal, and for small time windows, you compute this the back-azimuth. And if it's a moving source, you can see how the back-azimuth changes over time. For fun, we used it at our institute to measure roads that are passing our seismic station to see how they're moving and estimate their velocity. In a seismological context, it would be more useful, for example, to measure the rupture front of an earthquake, for example. Another point is wave type analysis. I already shown this a little bit in the beginning. So each wave type has a unique fingerprint in these 6C recordings. For example, we saw that Lough waves only cause a rotation on the vertical axis. So now we could analyze seismograms, for example, and identify the wave types contained in them. So for example, if we look for Rayleigh waves, here the colors show the likelihood that a Rayleigh wave is present in the seismograph. And we see that they occur in the later part of the seismogram as expected. And also we see the dispersive characteristics of the wave. So this method works quite nicely. Another really important application is tilt correction. So seismic recordings are often contaminated by tilt, especially at the ocean bottom, or strong motion recordings close to the source. And if you only have the seismometer recordings, then you can basically not correct for it. But there's a nice paper from Bernau et al. 2020 who showed if you have additionally a rotational sensor, you can directly measure this rotation and then subtract the tilt from your seismometer recordings. Another thing that we're working in Munich is structural health monitoring. So for example, here you can see a model bridge, and along the bridge there are several 6C installations. So now what you can do is you can compute the phase velocity at one location, and through repeated measurements, you could identify changes in the velocity, which could indicate a change in the health of the structure. So if you get a change in velocity, this could mean that the structure is damaged. Also, you can use this for monitoring buildings, for example, to get a more complete motion of the building during an earthquake. So in general, these single station 6C measurements are useful in any situation where you cannot set up an array or where it's difficult to set up an array. For example, at the ocean bottom, volcanoes, or in planetary sciences. So we're in Munich, we have expertise on all these applications. So if anyone's interested in learning more about it, I'm happy to discuss this later. But now let's get back to our inverse problem. Since this is a really new method, we wanted to test it in the field. So we performed a number of measurements in Munich. And at some locations, we also set array measurements to directly compare the results and to see if our new method actually does give reliable results. And today I will show you the location here. This is the location of the Theresienwiese, where we usually have our Oktoberfest. But in the days where we don't have the Oktoberfest, we have enough space to set up our array measurement. So here in the photo, you can see part of our measurement, where the red dots show you the location of the geophones. And up here is our 6C installation. So it really gets clear that an array needs a lot of space. Also, for the array, we set up 3 different rings with different diameters to record a wide frequency range. So this measurement really takes a lot of time. So now, to get the dispersion curve from the 6C data, we apply this equation, which I've shown you before. So we take our data, we filter them in frequency bands, and then we analyze this velocity for small sliding time windows. And then we sum the results up in histograms. And in our case, we take the maximum, we take the mode of the histogram as the velocity estimate at this frequency. And that's how we get then the dispersion curve. So as I said in the beginning, also from the array data, we can get dispersion curves, so that therefore we can directly compare the results for Rayleigh and also for Love waves. Now, the blue and the yellow curve are computed from the array data using 2 different methods. One is the high resolution frequency wave number analysis, and the other one is spatial autocorrelation. I'm not going to explain what these are, but you just have to know the blue and the yellow curve were computed from the array data and the green curve from the 6C data. So now when we take a look at it, we see that the curves overlap in a frequency range of about 7 to 20 Hertz. However, especially at low frequencies, we see large differences. So first of all, for the array, you have to be careful with the array resolution, which depends mainly on the geometry and the dimension of your array. So I show you here the lower limit of the resolution. So all the data points above this line should not be interpreted. But still, here in this range, we see quite large differences. And especially we notice that the 6C curve drops at a certain point. And that's something we would not expect. And we observe this for all of our measurements. So the question is, what is happening here? To answer this, let's look at the power spectral density of the recorded data. For blue is the seismometer data, and yellow is the rotational data. And there are a few things we notice. So first of all, the translational motions are larger than the rotational motions. That's something we would expect. But we would also expect that the trend that we see here in the translational data continues here in the rotational data. The problem is that at some point, the self-noise level of the rotational motion sensor is reached, which means that at this point, the rotational motions are too small to be recorded by the sensor. And that's why we're only measuring self-noise. And that's exactly where our method breaks down. So this means the sensor is still not sensitive enough to measure these small rotational motions. But anyway, we can still use the curve up to this point here. This, however, has the problem that we cannot invert to the desired depth of 100 meters, because for this we need lower frequencies. And that's why we additionally computed these H/V curves that I shown you in the beginning, because they're easily computed from the seismometer recordings that we have, and they give us information in the lower frequency range. So for the inversion now, we add these H/V curves with the Rayleigh and loft dispersion curve. Then we perform the inversion with, in our case, a TubeC software, which applies a neighborhood algorithm. And here you can see the resulting S-wave velocity profile for a 3-layer model. And you can see that the profiles from the different input data actually coincide quite nicely. So we see a velocity step at around 4-meter depth and one at around 20-meter depth. And also the velocity estimates within the layer coincide quite nicely. So with this, we can conclude that our new single station 6C method gives comparable results to array measurements, which is a great finding, because as we've seen, it's much easier to perform these single station measurements. In the next step, I compared it to a lithologic profile at the site to see if the inversion results make sense. And we can see that the upper step lies in the range of the groundwater table and is changed from sand to clay. And the second step lies again at the layer boundary between sand and clay here. So we do see a positive correlation. Now, when we take a closer look at the velocities within the layers, we see that at the surface they're quite low, between 200 and 400 meters per second, which is expected due to the sediments that we see here. So now the question is, do we see a wave amplification due to these small velocities? And I wanted to investigate this further using seismic simulations. In this case, I used the spectral element code Salvos. To do this, I first needed to create a 3D model. And in Munich, we're lucky because we have a lot of different subsurface information. So we have information about the depth of the main layer boundaries. We have information about the velocity within the layers, thanks to a 3D seismic survey. We have information about the shallow velocity structure, thanks to the microsonation study that we just did. And also we have attenuation values that were estimated during an earlier project. So we combine all these different information in this 3D model to do realistic simulations. So now first I wanted to investigate what influence does this small velocities have on the amplitudes. And for this I performed 2 different simulations. One with a low VF30 layer. VF30 means the S-wave velocity in the upper 30 meter. And I chose a value of 350 meters per second, since this is the average value I found in Munich. And I compared it to a simulation with a high VS30 value of 850 meters per second. And now when you look at the synthetic seismograms, you clearly notice that we have higher amplitudes in case of this low velocity layer. In this case, we have an amplification of 62%. So in Munich, we do have a moderate wave amplification, and this low velocity layer has to be taken into account for the further simulations to get realistic results. So in the next step, I wanted to perform a number of scenarios to estimate the distribution and also the maximum ground motion in case of an earthquake. But during my PhD, we did not measure any induced earthquakes at this new geothermal power plant. And that's why I went to the city of Poing, which is 15 kilometers east of Munich. And there we have also a geothermal power plant. And we have a number of induced earthquakes recorded, up to magnitude 2.1. And also the nice thing is that we have several seismic stations there, so we can directly compare the recorded data with my simulated data to see if the amplitudes that we simulate actually make sense. So in this case, I simulated the largest event in the area, which is magnitude 2.1, and it occurred at a 3 kilometers depth. And it had a left lateral strike slip mechanism with normal faulting component, which is consistent with the fault geometry that we have in the area. So one thing I want to point out that I only performed the simulations up to 10 Hertz, because if you want to simulate to higher frequencies, this would increase the computational cost significantly. And that means the simulation would run a lot longer. So let's take a look at the results. So here I compare visually the recorded data in orange and the simulated data in black for station TH1, which is the station directly at the injection well. And when we look at the three components, we actually see that they coincide quite nicely. So the onset is fitted quite well, and most important, also the amplitudes are fitted quite well. Now, to get a better idea about the differences between the signals, we applied this goodness of fit criteria after Christikova et al. 2009, who looked at the signals in the frequency time domain, and based on the misfit value between the signals, assigned a goodness of fit score. And a score of 0 means a poor fit between the signals, and 10 means an excellent fit. So now again, when we compare the signals, we see that for the north and for the Z component, we really get an excellent fit. And for the east component, we get a good fit. So we see some differences in frequency content, and not every wiggle is fitted perfectly. But like I said in the beginning, it's most important to match the maximum amplitudes, and that's what we're doing here quite well. So I would say we do get realistic results with our simulations. Another nice thing that can be done using the simulations is to compute so-called shake maps, which show us the peak ground velocity at the surface. So this shows us the distribution of the ground motion. So in this case, these yellow areas would be most affected. And we see that it actually coincides quite nicely with intensity reports that were filed from the population for this event. Also, from the map, we can read the maximum simulated PGV value, which in this case is 2.2 millimeter per second. And when we compare it to some norms that we have in Germany, which says that for ground motion below 5 millimeter per second, damage to buildings is unlikely, we see that this event was still uncritical. Another thing I want to point out is that the station TH1, which for this event was the only monitoring station in the area, does actually not lie in the area of largest ground motion, which is down here. So having only few seismic stations, it's nearly impossible to measure the actual maximum ground motion that the event induced. And therefore, you see, seismic simulations can be really useful to give you additional information to your recordings. So now that the simulations are calibrated, I can easily apply them to other locations around Munich. And for example, already use it in the planning stages of a geothermal project to estimate what could be the largest ground motion that we expect and find the maximum tolerable magnitude, for example. With this, we come to the last point, the network optimization. So here I show you the map from the beginning again. And as I already mentioned, we have relatively few seismic stations for monitoring all of these geothermal power plants at the same time. Plus, for our new geothermal power plant, we're really sitting in the middle of the city, so we have high ambient noise levels, which makes it difficult to record small magnitude events. So the question is, how can we improve our monitoring? For this, we developed a new software called PyNet Op3D, which is based on the work of Hart and Scherbaum, 1994, who performed a network optimization for northern Switzerland. And this code is based on simulated annealing. This code is freely available online, so everyone can use it. And I'll just demonstrate how it works. So first of all, you need a number of input data. One, the velocity model, which we already got thanks to our simulations. Then really important is a noise model to estimate the noise level at the different sites. And I constructed such a noise model for the Munich area. And you can clearly see that here in the city center, we have much higher noise amplitudes compared to the surroundings. And also the high amplitudes are mainly confined to the streets. But also within the city, we see small points of lower noise level, which could be suitable for placing a seismic station. Then in the next step, you can implement all the existing stations that you already have, so surface and borehole stations. And in our case, they're mainly located close to the injection wells. Then you define a synthetic earthquake catalog, and for simplicity, we put them at the injection wells. And then in the end, you overlay it with a grid of possible station locations. And the code will then pick those locations from the grid, which make up your optimum network. So before I performed such an optimization, I actually wanted to see what's the performance of my existing network. And the code can also evaluate this. So I implemented all the existing stations that I have in the area, and I simulated a magnitude 1 event because this is the magnitude of completeness that we want to reach. And now what the code can do is calculate the number of P-wave detections in case this event occurs at any of these pixel locations. So as you see, if the event occurs here in the middle of the network, more stations are able to detect it compared to if it occurs on the edge or outside of our network. So this observation makes sense. Now, when we take a closer look at our inner city geothermal power plant, which is here, at some locations, we would only have 2 detections, which is, of course, not enough to locate the earthquake. Then we can also look at the uncertainties for the location of the earthquake, so for the epicentral and vertical uncertainties. And here we have some recommendations that say for induced earthquakes, at least magnitude 1 earthquakes should be located with an epicentral uncertainty of less than 500 meters and a vertical uncertainty of less than 2 kilometers. But when we look at the map, we see this is, again, only the case here in the middle of our network, while in the surrounding of our inner city geothermal power plant, we have quite high uncertainties, and also for the vertical uncertainties. So the reason for this is well, here in the Northwest, we have less stations, so we kind of have an azimudal gap. But we also, this is where our inner city starts. So we have high ambient noise levels, which result in low signal to noise ratios, which give us high uncertainties. So we definitely have to improve our network in the city. And therefore, I performed a first optimization run. So I input all the data that I've shown you before, and then I tell the algorithm, okay, I, for example, want to place 5 new stations. Where is the optimal location to place these stations? Then the algorithm performs the simulated annealing and returns me these locations here, the pink triangles. And with these 5 additional stations, we already see that the number of P-wave detections increased, but the epicenter and vertical uncertainties really only slightly increased. And in fact, I tested up to 15 new stations and still I was not able to reach the recommendations. And it's because, like I said, we have high ambient noise levels. So it doesn't matter where in the city you put your stations, still the signal to noise ratio is low and therefore we have high uncertainties. So we need to improve our signal to noise ratio. And this can be done, for example, using borehole stations. To test this, we installed a 180-meter deep borehole station in the Munich city center. And when we compared it to the overlying surface station, we saw that the noise level reduced by a factor of 10, which is actually quite a lot. So now I perform the same optimization as before, but now I say I want borehole stations because the ambient noise level is much lower there. Again, the algorithm performs the simulation as the optimization as before. And this time it returns these 5 locations, the dark blue triangles. And with these additional borehole stations, we now get much higher number of P-wave detections, and we easily reach the recommended thresholds. So with this, it gets clear that for the monitoring in urban environments, borehole stations are required. The drawback is that they're really expensive, so you cannot just install a high number of borehole stations. So with this, we can now answer these 3 questions. So first of all, we saw that our new single station 6C method allows a fast site characterization, which is really nice, especially when you're working in a city where you cannot set up an array. And we found a moderate wave amplification in Munich, which has to be taken into account. Then we saw that seismic simulations are useful to estimate the distribution and the maximum ground motion in case of an event, which is useful already in the planning stages of a geothermal project, but of course also after an event. And by comparing the simulation results with real recorded data, we found a good comparison. And in the end, we saw that we have high ambient noise levels in Munich, and therefore we need borehole stations to improve our network. And with the network optimization code we have, we can know the optimum location for the new stations if we want to place them. So with this, I would like to conclude that the project results have implications for future geothermal projects, since they facilitate the seismic risk assessment during the planning stages of a project. They improve the seismic monitoring during operation, and also they facilitate the evaluation of shaking effects after an event. And with this, I'm at the end. If you're more interested, you can download my PhD thesis here, which contains all the papers with the results that I just presented. And I hope I was able to convince you that rotational seismology is really a cool thing. So nowadays, a lot of people only talk about distributed acoustic sensing, but actually rotational motions have a large potential. And if you're more interested in this, I would be happy to talk to you about it. And I would like to say we have 4 sensors, 4 of these blue site sensors at the Institute. So maybe we could come up with an interesting project ideas and do some measurements together. Thank you for your attention.
Sabrina, thanks a lot for this very clear and very nice talk. And of course, we are interested, and we come and we will speak with you about rotational seismology, because it's definitely part of the future in seismology. Questions in the chat, questions in the audience, please don't hesitate.
I'm not a seismologist, but I'm curious to understand, why is this biggest earthquake you are using for your study? Why does it show this mainly strike-slip mechanism, if it is related to the circulation of water underground? I would expect some more gravitational origin for that mechanism.
You mean this pattern? Or so you mean
I mean the focal mechanism of the earthquake. Yeah.
Yeah. So I mean, it mainly depends on the stress field that we have in the Munich area, which mainly comes from the Alps. So we have almost perfectly north-south pressure, but the faults are direct. So the faults are oriented like this. So actually, this has an almost optimum orientation for slip. And like I said, it is almost perfectly strike-slip. It has a small normal faulting component, but mainly it's strike-slip. And I would say you do see it in the pattern, like here.
Okay, so it's related to the regional field of stress?
Yes, and through the circulation, at some point it can happen that it reactivates the fault. And yeah.
Thank you. Next question, please. The chat, other questions? No? Yeah, Elena.
Thank you for your presentation and congratulations for your work. I never been in Munich, but I was wondering how the buildings are there, if they are with a lot of height.
Sorry, what's there?
If they are tall.
The buildings are, well, not super tall, so not much more than here in Barcelona, but I mean, the buildings are not constructed for earthquakes. So a magnitude 2 earthquake, people in Japan or California will laugh about it. But for us, we're not used to earthquakes, and all of a sudden you have a magnitude 2.5 that you can feel. Maybe historic buildings could already get cracks or something, yes.
I was thinking on the drawback of the rotational station, that in the lower frequencies, they are not sensitive enough. But if the buildings on Munich are not tall, then it's not important. What do you think?
So first of all, I'd like to say it's a broadband sensor. So in theory, you can measure these low frequencies, but the problem is the amplitude of the rotations. So for studying ambient noise, the amplitude decrease in this case with the frequency, and at some point they're just too small to be measured. But if you have strong motion recordings, you can definitely record also the smaller frequencies. And we also have some strong motion rotational sensors that we were testing in buildings, for example, and they are perfectly measuring these frequencies.
Thank you.
More questions? Don't hesitate. In the chat, I don't know. Here in the audience. Yeah, Pilar.
Thank you very much for the presentation. It was super clear. I think you said the temperature of the reservoir, but I don't remember. What is the temperature?
About 100 degrees.
100 degrees. And with 100 degrees, you can, so you use the energy for electricity generation and heating, or only for heating?
No, really, it's mainly only for heating. I think there was one geothermal power plant more in the south, which at some point used it for electricity, but it doesn't really make sense with these temperatures. It's more economic to use it for heating.
Okay. Thank you. And a second question is related to the rotational sensors. So I know they are super expensive.
Yeah.
I don't know if there is any advantage to have an array of rotational sensors or not. Just with one, you can do everything. Or what is your opinion about that?
Yeah,
if they become cheaper, I don't know if it will be useful to have an array or not.
So with this application that I'm doing, so site characterization, it's sufficient to have one sensor. You can place it one, do a measurement, then go to another location and so on. But for example, for application of moment tensor inversion, which we were working on volcanoes, It was shown that if you have an array of rotational sensors, you will need less stations than if you have an array of normal seismometers. So you still need an array, but you need less stations.
Yes.
Great, thanks for the talk and inspiring. For what I see is that the rotational sensor doesn't substitute the conventional sensor. For what I see, usually the better idea is to have both on a single setup. Is that correct?
Yes, so for 6C, you need also a seismometer. What it substitutes is more stations, so you don't need to set up an array. But yes, you need both in combination. Yeah.
So the full wave field is being described by 3 translational motions. That is the conventional sensors we have, and then the 3 rotational components. And
yeah, so that's the idea also to build them both in one sensor. For example, our strong motion sensor does have both components in one, but this was, yeah, it's 2 separate ones.
we are doing monitoring in a mine and in structural health monitoring and so on. And we would love to have some rotational sensors to also test them and play with them there. But they're really expensive. You said Munich has 4 sensors?
Yes, we have 4 sensors. If they're always working at the same time, it's a different question because they're quite new. They also sometimes have some problems and we have to send them back to maintenance. But in general, we have 4.
The frequency band, so you're using, due to the self noise, you're using 1 to 10 hertz. That was
So in general, it's from 0.01 to 50 hertz. So it really depends on how large are your amplitudes, if you can measure them or not. But yeah, the experience in the city is that below 5 hertz, you're not measuring anything. So if you go to a quiet site with the sensor, you will not measure. Unfortunately, you will not measure any noise. So it's really an application for the city.
the stabilizations, they need quite some time to stabilize, or is it easy install like in conventional sensor?
No, it's really fast. You just place it, orient it, and can start.
Water? Are there any efforts for OBS systems like this?
Yes. I know that my colleague is also working on this with some collaborations. Yeah.
I'm in a project where there is an effort to design an OBS, rotational OBS. Part of this project was Blue Size, but they stopped. They closed, and I don't know how it continues. It is on the way. I don't know about other efforts. More questions? Lara, is there a question in the chat? No? Okay, Sabrina is here in the Institute. She has her office in the 3rd floor. Please, questions may pop up later. Don't hesitate. Go into her office and speak to her. She speaks perfect Spanish. And so also you can do it in Spanish. No need to do it in English. Thanks very much for everything. Thanks.